Sure. So today, Yuko Kuroki at Chantai has given us a seminar about sequential decision making. So it's about two things. One is for efficient quality clustering, and another is best of post-model for contextual bandits. Yeah.
Yes, thank you very much for invitation and kind introductions. I really appreciate this opportunity. I'm happy to present my recent work about advancing sequential decision making, efficient querying in clustering, and best of both worlds for contextual bandit. So my name is Yuko Kuroki from Chantai Institute, located in Turin, Italy. So yeah, we are close. So yeah, thank you for Liam for this invitation. So yeah, before going to the detail, I just first describe today's content, also mention about the credit for my course. So this talk first part will be devoted to the best of both world algorithm for linear contextual bandit. This is appearing this year's AirStats. This is joint work with Alberto Rumi from University of Milan, and Tyler Tsuchiya from University of Tokyo, and Fabio Vitale from Centa Institute, and Niccolo Cesabianchi from University of Milan. Then second part is devoted to the query efficient correlation clustering with noise oracle, which will be appeared in New Lips this year. This is joint work with Atsushi Miyauchi from Centa Institute, and Francesco Bonchi from Centa and Eurecat, and Wei Chen from Microsoft Research. So common concept is multi-armed bandit. So first part is classic linear contextual bandit, but advanced topic includes the best of both worlds algorithm. And second part is more on combinatorial nature. So we combine the combinatorial optimization and multi-armed bandit framework, especially on best term identification, which I will describe later. So first part is best of both worlds algorithm for linear contextual bandit. So first, I will describe a general framework for multi-armed bandit as a classical decision-making model. So multi-armed bandit, we are given the K action called arm. Then environment determines the loss to the arms, so denoted by LT. LT is a K-dimensional real vector. So each component corresponding to the loss for each action at each time step T, which is hidden to the runner. So the online game will describe as follows. At each time step T, runner select an action, single action AT, from the K positive action, and it got the loss LT of AT. So here, we consider bandit feedback. That is, runner observed only the loss for the chosen arm, LT of AT, is revealed. So for other actions, we cannot observe the loss at the current round T. Here, the goal is to minimize the expected regret, cumulative regret, against the best action in hindsight. So here, RT, regret, is defined as the difference of cumulative loss of the runner and the cumulative losses of the best action, where A star is defined by the minimizer of the cumulative loss. So in this work, we consider the contextual information into the bandit framework. So here, we say we often have access to contextual information in real world and in various domains, such as online advertising or medical diagnosis and finance. For example, consider recommendation system. So here, as a contextual information, we can get the additional information about the user's profile or past purchase history. Then here the goal is to utilize such contextual information for providing more personalized product recommendation. So also there are a lot of huge history for contextual bandits. There are many formulation and mathematical definition for contextual bandit, but here we'd like to focus on the following setup. At each time step T, environment determines the loss vector, theta TA. This is a d-dimensional real vector for each action A. Then, independently of the choice of loss vector, environment draws a context vector. This is xt. This is again d-dimensional vector. So we consider that this context vector is generated from the unknown distribution D, but this distribution is fixed over time horizon or the time horizon. So then learner observes the current context xt. Then using this information, the learner chooses the next action AT from K action space. Then learner encodes and observes the loss function depending on the current context and chosen action. Then,
That's the question. So
Yeah,
the
yeah.
context, is context arm specific or is it shared by all the arms?
Yeah, thank you very much. So there's several type formulation, but here it's XT is independent, but there is an equivalence problem formulation. So we can consider the arm dependent context. So actually it's some equivalence with extra dimension D, but here we consider in program setup. So context vector is general. Yeah.
Thanks.
Yeah. Thank you very much for question. So I really appreciate the question. Yeah.
Question. So what is the relation between theta TA and LTXTAT? Is it the same?
Yeah. We will describe the definition of the LTXTA in the next slide.
Okay.
Yeah. So let me. Yeah. Just please wait. Yeah. Please feel free to interrupt at any time. Yeah. So okay. So yeah. So here's a for the loss function, I will describe the detail next slide. Then the goal is to minimize the expected regret against the optimal policy by star rather than the fixed best action. So here, optimal policy is defined by the defined as following. So calculation phi is denoted as a set of all deterministic policies mapping from the context space to action space. Yeah, where the calculus X is the context space, d-dimensional context space. So here, we will describe the definition of the loss function depending on how the loss vector theta is generated. So we consider both adversarial and stochastic regime. In adversarial regime, loss function LT of XTA is defined by the linear product of context vector XT and theta TA, where the theta TA is chosen by adversary. In the stochastic regime, so here we assume that there exists a fixed vector theta A for each action A. So this is fixed over the time horizon but unknown to the runner. Then loss function of the LT on XT and A defined by the linear product of XT and this theta A. And also we have the noise term, which is bounded and zero mean noise. So we also consider the intermediate regime between adversarial regime and stochastic regime. This is called corrupted stochastic regime. So here we again assume that there exists a fixed vector theta A for each action A, but there is corruption. We consider corruption. Then this corruption is parameterized by the C. We call it corruption level C. This provides a upper bound for all the corruption, cumulative corruption. So which describes the difference between theta TA and fixed vector theta A. Yeah, then loss function again defined as follows. So we see that the corruption level C, when corruption level C is equal to 0, then this becomes a stochastic regime. While the corruption level C is very large, like order T, then this is equivalent to the adversarial regime. So here, yeah, we our aim is to derive the best of worst algorithm. So what is the best of worst algorithm? So here is a research question. Can we establish an algorithm achieving optimal rate in both stochastic and adversarial regime without any prior knowledge of the environment? So you know, classic UCB, upper confidence band algorithm type algorithm can achieve the optimal rate like log t in the stochastic regime. So while in adversarial regime, so exponential type algorithm exp3 can achieve the square root t regret bound, but you know, UCB algorithm cannot achieve the optimal rate in adversarial regime. So this will incur linear regret in adversarial regime. While exp3 algorithm can only attain the order square root t regret 1 in stochastic regime. This is suboptimal. So best of both world algorithm aim to guarantee the both nearly optimal rate, like in stochastic regime. So we aim to establish the polylog t regret bound in stochastic regime. At the same time, we also want to guarantee the square root t regret bound in adversarial regime without any prior knowledge on the environment.
Sorry, and I guess the motivation there is because you never know when if you want to apply it in a certain setting, you don't know whether you are in an adversarial or stochastic regime.
Right, yeah. So yeah, in the real world, so if we use export 3 type algorithm, this is too pessimistic. Its environment relatively stationary and easy. But while if we rely on the UCB type algorithm, but the unknown environment has some arbitrary changes in adversarial environment, which is not stationary, far from the stochastic environment. So we will incur a large regret. So we best of both world algorithm wants to wish to establish a kind of robust regret bound for each whenever the environment is a stochastic regime. So we automatically achieve the nearly optimal rate, log t rate. If the environment is adversarial regime, then the algorithm will automatically adapt to the environment. Then still can guarantee the square root t regret bound. This is what we want to achieve.
Can I ask a question, please?
Yes.
I was just wondering because the optimal policy, like the competitor class, isn't it normally defined differently in the stochastic regime and the adversarial regime?
Excuse me. So could you
Sorry,
please?
the competitor class, the optimal policy you compared the regret against?
Yes. Yes, optimal policy is, this is the common definition for both stochastic and adversarial regime.
Okay.
Yeah.
Okay, thank you.
Really? Because in adversarial setting, you just compare it against the arm, keep choosing the single arm, right? It doesn't.
Yeah, that's
change
kind
it.
of what I thought.
Is it? So you allow that competitor to change switching between arms. Is that?
Yes. Here we consider the deterministic policy class. Then optimal action is now defined by policy. This is a mapping from the contextual space to action space.
I see.
Yeah.
So
It could include that.
no. So like in adversarial, like if there's no context, right? That you always you compare it against the policy that always choosing the single arm.
Yeah.
right? Isn't this?
Yeah, I'm just saying that that's included in the set of all deterministic
But
policies.
the combinatorial is much more stronger than that, right? So which gives you the difference regret bound.
Yeah, that's yeah.
Okay.
So I guess that's the question.
Yeah, so yeah,
But still, you would just compare against really strong competitor.
yeah, optimal policy is deterministic. So
As long as it is deterministic.
yeah, given the context X, so this pi star always returns the same action. So this is a deterministic policy.
Yeah.
Yeah.
Okay.
So hope that this is clear. Okay, yeah. Okay, so yeah, thank you for questions. Here is the informal main contribution. So we have two components as a main result. So first result is the red one. So in the adversarial regime, so we have the regret bound being square root dkt, where d is the dimension of the loss vector and context space, and k is the number of action, and t is the time horizon. While at the same time, stochastic regime, so we have the dk polylog t regret bound in order. Yeah. Then second component is so we say this regret bound as a data dependent bound because this lambda star depend on the data dependent quantity like a cumulative second moment for the loss incompasses algorithms, which we'll specify later in the later slide. While guaranteeing the polylog t in the stochastic regime. So yeah, first result rely on the follow the regularized reader framework denoted by FTRL. So in this framework, at each round t, the runner maintains the probability distribution, so PT, given the context xt, that minimize the estimated cumulative losses up to previous round, and the convex regularizer. So where L tilde xt denoted the loss vector for each action, where theta tilde is some estimate for the unknown loss vector theta SA. So as a convex regularizer, we select the Shannon entropy regularizer defined as follows, where eta t is the adaptive running rate, which should be sophisticated design. Yeah, technical highlights includes how we design the eta t, and also I omitted the detail of how to construct the loss estimator, but here we consider the contextual information, contextual vector, but here, so due to the estimation of the covariance matrix, so theta tilde can be biased, but this bias estimator can still valid to have a reasonable regret bound, because the bias term due to this estimation comes from the covariance matrix can be vanished when the time horizon t is large enough. So yeah, then I'll focus the description describing how to design the adaptive running rate. So here, so we use the entropy dependent running rate. So we update the eta t inverse like that, where this blue part corresponding to the cumulative term of the Shannon entropy, where PS given XS is a minimizer of the FTRL. So this blending rule is enable us to control eta t inverse. So in adversarial regime, eta t inverse would become order square root t, while in the stochastic regime, so if the environment is stochastic regime, eta t inverse would become order t. So this property is crucial to analyze further. So essentially, we rely on the standard FTRA analysis. So we aim to bound the expected regret, but here so we have the context information. So expect regret with respect to the fixed sample x0. So this is the independent sample from the unknown contextual distribution. Then we have the mainly two terms. So here, one term and second term. So second term is related to the variance of the loss estimator, but this can be, but both terms can be balanced using this property to have the desirable regret bound. So this analysis is inspired by the current recent work by Ito, Tsuchi, and Honda. This is originally designed for another bandit variant called learning from graph feedback, but this framework can be generalized for other variant. So we first show that this strategy can be adapted to our contextual bandit. So here is a technical main result.
Well,
Yeah.
could you go back one slide? So what is PS? Probably TS was the blue parts. What is
Blue
the
parts.
P is measured
Oh,
against?
sorry, yeah. So PS of given XS is the minimizer of the FTRL.
I see.
Yeah, then
So if they follow the reader, just have assigns the equal probability to each arm, it gets learning rate smaller or larger? So if the entropy gets large, right? So if this PT is more close to unique, uniform, then
yes.
the entropy gets larger so that it's
So
Plus-
Shannon entropy regularizers inspire this. So we aim to FTRA suggests a single. So this means we have some extra costs. So we need this should be Shannon entropy regularizer becomes up to uniform distribution has large penalty.
So when does it reduce to
Reduces slower.
is lower or
Because
larger?
they're inverses, you're adding.
Is that a bit
Yeah.
So if the follower reader really
whole thing is smaller or less, it's smaller update of beta.
which gives a small update in beta.
Intuitively, I would think that actually for more uniform relief there, you would actually get larger updates. You would kind of base it more on the current information in a way. Or perhaps I'm interpreting that wrong.
So is there any intuitive explanation for this, like this update rule? If FTRL only selects one arm versus FTRL just gives the same amount of probability.
Can you hear us? Can you hear us?
Yes. Sorry. So negative Shannon entropy regularizer is already here.
Okay.
Missing.
So if FTRL, the P of T is uniform, so follow the regular leader can select any arm, which means the entropy gets larger, right?
Yeah.
So in that sense, this learning rate gets larger or smaller? Oh, because this is just the step size. So
Yeah, it's just a small update.
no, I mean the inverse is for the step size. So if the entropy gets larger, it increases. No, it doesn't increase much, right?
Yeah.
Which means that they use more past. Right. Yeah, it was very confusing.
Yeah,
In adversarial regime, you would expect higher entropy, I guess,
yeah, it's yeah.
or slower.
I see it grows slower. Yeah.
Yeah, in the stochastic regimes, algorithm wants to focus on the single arm, single optimal arm. But adversarial regime, we still need to have some exploration term.
I see.
You want to mix.
Yeah.
That makes sense.
So yeah.
So I had another question. Because you're estimating the covariance as well. Are you assuming that the noise is like sub-Gaussian or something for the stochastic regime?
No, actually, so we as a contextual distribution, we only need the assumption on the minimum eigenvalue, some bounded minimum eigenvalue. This the final result includes a minimum eigenvalue of covariance matrix. So we need to make it a positive value. Yeah.
So that's to guarantee invertibility or?
This.
Guaranteeing invertibility.
So we have some diversity, kind of diversity. We need kind of diversity on the distribution, context distribution.
Ah, I see. So you just okay. Yeah.
And but I mean, sorry, what about in the stochastic case? What about the additive noise? There's also an additional noise. Do you add?
Yes. In the stochastic regime, so epsilon t should be bounded.
It should be bounded loss. Okay, yeah.
Yeah, I didn't detail, but loss vector should be this loss function, loss value should be -1 to 1.
It's also bound.
Yeah.
Yeah, we need the bounded zero-mean noise. So we cannot deal with our sub-Gaussian distribution. We need some additional steps to deal with our unbounded distribution.
Yeah, that makes sense. Thanks.
Yeah, thank you. Thank you for questions. So again, this is main result. So by FTRA with channel entropy, so this will achieve the square root of t for the adversarial regime, and in the stochastic regime, so we have the polylog t divided by the minimum suboptimal gap over the context space. We also have the lambda mean of the covariance matrix. Here we also have the result for corrupted stochastic regime. So we see that this is bounded as a regret for the stochastic regime. And also this additional term is square root of C and regret for the stochastic regime. So this rate is optimal. Yeah. Where C is a corruption level. So this bound recovers the best known result in the adversarial regime up to log factors. Yeah, here is so far, this is all for the first result, and we are going to the second part. Or if you have a question, you can take. Then okay. So second result discuss the benefit of data-dependent regret bound. So rather than the time horizon t, so we consider more smaller value in the regret bound. For example, so we consider cumulative loss of the optimal policy. denoted by L star. So this value can be much smaller than the actual T. So another example is the cumulative variance of a policy denoted by lambda bar with respect to the average vectors theta bar. This variance, cumulative variance, might be much smaller than actual time horizon T. So here, we aim to best of both worlds bound, which depend on such a data-dependent quantity. So we rely on the optimistic FTRL framework rather than the standard FTR framework. So in the optimistic FTR framework, the runner has access to the loss predictor denoted by MTA. This is also called hint vector for each action A at round T before making the next action. So using this hint vector, so predictable loss MTA, so we kind of adapt FTRL. But here we need some additional more complex components. So we need to deal with continuous exponential weight. Then to satisfy the stability condition, which is called data-dependent best of data-dependent stability, proposed by the last year's court. So here we rely on this black box reduction. So I only describe the overview. So we design some optimistic FTR algorithm, so which translate to the best of both world algorithm with some stability condition. So sorry for keeping technical detail, but here is the main result. So as a main theorem, we derive the following regret bound, which achieves the polylog T in the stochastic regime, while also the decay square root lambda star in the adversarial regime, where lambda star is the cumulative variance of a policy with respect to the predictable loss sequence, MTAT. And as a corollary, so we have the first order and second order regret bound, where the lambda L star denotes as the cumulative loss of the best policy, and lambda bar is the cumulative variance for the loss incurred by the algorithm. So in the regret bound, we achieve the minimum of this quantity. So compared with the result for solely adversarial regime, we only have the extra square root D in adversarial regime, while we can also guarantee the polylog T in the stochastic regime. Then for the choice of the loss predictor, so we use the online optimization method, which is considered in the linear bandit. But we can use a similar technique for contextual bandit. Then this allows a single algorithm to achieve the first and second order bound simultaneously. Yeah, here is a summary for my first talk. So we provide the first best of both world bound for linear contextual bandit. So yeah, before moving to the second part, if you have a question, I'd happy to take some questions.
Why you think of second order?
Mm-hmm.
How do you interpret the second order regrets? Like you tell it is the variance, but how we should interpret it? Is it the variance?
Like a lambda bar?
Yes, yes.
Yeah, this is kind of close to the maybe flavor of a stochastic environment. Like so, instead of moving the arbitrary sequence, so there might exist a case where the loss function, loss value has some small variance with respect to the this theta bar, average vector. Yeah, this kind of adaptive setting on the stochastic environment.
I see.
Yeah. Thank you. Okay, so yeah, I'd like to move on to the second part. The second part is based on the recent work entitled Query Efficient Correlation Clustering with Noise Oracle. So here we discuss the general clustering framework. So correlation clustering is one of the successful formulation in theoretical computer science, also data mining. In correlation clustering, we are given a set of n objects and pairwise similarity. The goal of correlation clustering is to cluster the object so that the similar objects are put in the same cluster and dissimilar objects are put in different clusters. Then the objective is to minimize the falling cost. So here's the first term corresponding to the penalty when suppose that if this x and y are very similar, dissimilar, but we put these two objects into the same cluster, then we need to incur the higher cost. Yeah, then second part is kind of inverse. So even when the object x and y are very similar, but if we put these objects into the different cluster, then we need to incur higher cost. So this is a minimization problem is characterized as formulated as a combinatorial optimization. And there are a lot of results. There is some benefit in the data mining perspective. For example, there is no need to know the number of optimal clustering beforehand, unlike k-means. So correlation clustering formulation allows any number of optimal clustering. Also, there is no limit on the size of the clustering. Also, this formulation is effective when the data is very complex, but we can only have the pairwise judgment of similarity or dissimilarity rather than the quantitative distance information. So we don't need to consider the Euclidean space, just we need the information about the pairwise comparison of the two objects. So from the theoretical computer science, there is a lot of approximation result. So for example, Charikan, Gulsubami, and Ross presents APX hard. This means that we have no hope to have the polynomial-time approximation scheme. Nevertheless, there is a lot of positive result, like a seminar work by Iron, Charika, Newman presents a very elegant greedy algorithm, which provides 5 approximation for general weighted case and 3 approximation for the binary weighted case. There are another approximation result based on the linear programming was SDP type algorithm, but from now we will focus on some greedy type algorithm presented by Quick Cluster. So although there are rich history for computational perspective, but in practice there is some issue. So first, preparing the similarity function involves a costly measurement. Like given n items to be clusters, we need n squared similarity computation to prepare the input for the optimization problem. Moreover, computing the similarity might have additional expensive, like human effort or financial resource besides the mere computational cost. To mitigate such a practical issue, there is some work to consider the query efficient way to have a reasonable solution guarantee for correlation clustering. This is kind of active learning framework. So we are given a budget of T cluster queries. Then we can still recover a solution with some approximation guarantee, like 3 approximation solution with additive error. But this is for binary case. So yeah, such existing will still have some limitation. So first, they only consider the binary similarity of 0 or 1, while the similarity between the two objects is often non-binary in real-world scenario. For example, protein-protein interaction networks, the strongness of interaction of two proteins can be represented as a non-binary value. Also consider the entity resolution. The likelihood of matches of two objects can be represented as a real value rather than being just binary 0 or 1. Moreover, existing work assumes access to a strong oracle that returns the true value of similarity 0 or 1, while evaluating the similarity might be inherently noisy due to error-prone experiment, noisy measurement, or bias judgment. So to meet, So here is our proposal to resolve such a limitation. So we focus on the challenging scenario where the underlying similarity measure can take any real value in 0 to 1 rather than just being binary. And we can only create a noisy oracle that provides inaccurate evaluation of the weighted similarity. The goal is to devise clustering algorithms that performs as few queries on the similarity as possible to an oracle that returns noisy answers to the true similarity. To this end, so we utilize a multi-armed bandit framework, especially of the best arm identification framework. So we formulate our correlation clustering with noisy oracle as a pure exploration of multi-armed bandit problem. At each round T, the runner will pull one arm from the action space. So here in the correlation clustering setting, the runner will query one pair of the elements from all the possible pairs. Then after pulling the arm, then runner can observe the random feedback xt of E, which is independently sampled from unknown distribution with mean S of E. So we consider the Bernoulli distribution or R-sub-Gaussian distribution as unknown distribution. Following the standard formulation of best term identification, we propose two settings. So first setting is called fixed confidence setting. So in this setting, so given a confidence level delta and additive error epsilon, the runner aims to guarantee that the cost of the output of clustering is alpha approximate solution up to additive error epsilon holds with probability at least 1 minus delta. Here, the evaluation metric of an algorithm is the sample complexity. That is the number of queries to the oracle the runner uses. Another setting is called the fixed budget setting. So we are given a querying budget T, then the runner aims to maximize the probability that the output of the clustering is alpha approximate solution up to additive error. So due to the time limit, I only provide the result for fixed confidence setting. So compared to the previous formulation for the standard best term identification of pure exploration of combinatorial bandit, alpha equal 1 corresponding to the previous formulation. But here we deal with the NP hard combinatorial problem. So we generalize the existing formulation for dealing with NP hard problem. So here I want to mention some existing issues of the existing algorithm for pure exploration of combinatorial multi-armed bandit. So existing combinatorial multi-armed bandit aim to find the the best action, combinatorial action, like size K subset or minimum spanning tree or maximum weighted matching or shortest path using the sequential random feedback. But there are a lot of framework, a lot of algorithm, but they don't apply to NP-hard problem because here in the pure exploration framework, we needed to design the stopping condition where the algorithm can stop, then verify the current best estimate, best action is actually the best action in terms of the true unknown edge weight or unknown reward, unknown loss function, unknown loss vector. So in existing algorithm rely on the kind of confidence bound type algorithm, but here, so we to establish the stopping condition, the exact minimization oracle or maximization oracle is crucial to guarantee the output. But this framework cannot be used to deal with NP-hard problem. So key idea is to utilize the property of offline algorithm. So here in correlation clustering, so as I introduced, quick cluster is proposed as an offline greedy type algorithm. So we utilize the property of this offline algorithm. So let me describe this offline algorithm. So first we pick the pivot denoted by PR from the object. Then we see the neighbor. So if the neighbor has a higher similarity, then we create the cluster within these neighbors. The threshold is 0.5. So yeah. So offline algorithm can utilize this similarity value, but even without knowing similarity value, we can design an online version of the quick cluster. So we also have a benefit for the approximation guarantee. So even when the case where we don't know the similarity value in advance, by accurately estimating the mean similarity between pairs, we can maintain the approximation guarantee of 5 of a quick cluster in the offline setting, like noise-free setting. Yeah, so here is a higher level algorithm sketch. So we combine the quick cluster classic approximation algorithm with threshold bandit. The threshold bandit technique is employed to identify high similarity pairs. Then we conduct kind of pivot algorithm inspired by the quick cluster, which is a greedy procedure based on the high similarity pair. So we conduct on the estimated high similarity pairs. Now, however, so if there exist pairs like which exactly close to 0.5, a naive threshold bandit algorithm may not guarantee termination. So this is a unique problem issue in the threshold bandit, but here is a unique feature. So output accuracy is still guaranteed even with small misidentification for pairs with similarity close to 0.5 in correlation clustering. So this is a unique feature in our case. Then key designs is to prevent unbounded sample complexity. The threshold bandit step is designed to allow some misidentification of such pairs. And here is a theoretical result. So the proposed algorithm guarantees a 5 approximate solution with additive error, epsilon, with probability at least 1 minus delta. Then sample complexity is characterized upper bound by follows. So where delta tilde x y denotes approximately distance from the similarity value and 0.5. And delta mean is the minimum gap of this similar distance from the between the similarity value and 0.5. So this bound is much better than the naive uniform sampling method, which requires the n2 squared divided by epsilon squared log n over delta. The significant term related to log delta inverse is characterized by this gap delta xy, which represents the distance from 0.5. Yeah, this is a conclusion. So we studied the online learning framework, correlation clustering with initially unknown similarity and noise feedback. We introduced novel online learning formulation rooted in the pure exploration of combinatorial multi-armed bandit, an algorithm whose sample complexity, which is number of queries, required to find a clustering whose cost is at most 5 approximate solution up to added beta epsilon with high probability. So we note that our algorithm are first example of pure exploration of combinatorial multi-armed bandit for NP-hard offline problem. The future work might be deriving information theoretic lower bound of this problem for NP-hard offline problem. Another direction might be investigate variant of correlation clustering or dealing with a non-uniform noise scenario. Yeah. Thank you very much for your listening.
Thank you for the presentation. Yeah, if you have any questions in the room, maybe from Zoom. Okay, so I have one question. So you mentioned this translation in graph theory, graph structure. So at the end of the day, how the algorithm works, like, is it so at each time this quick cluster tries to evaluate this similarity, and you just pull that pair to get the similarity? Is that true, or is it more special with how to select which arms to choose at each?
Yeah. The main algorithm conduct is two parts. So first step is the threshold bandit. So we just identify the high similarity pairs, which has a similarity value rather than 0.5. But yeah, we consider some epsilon added beta. Then second part is run the quick cluster, but we can have another variant, like we can mix the quick cluster and threshold bandit. So each quick cluster will have some phase algorithm. So each phase we can conduct threshold bandit framework. So this the number of phase of the quick cluster is much smaller than the total object n. Then this algorithm works better than just a two-step algorithm.
I see. So the current version is that you just first run threshold bandits to get the sense of which pair has more similarity rather than 0.5.
Yeah, right.
Then
So
use this offline method too.
yeah, right. This algorithm corresponds to this sample complexity, but if you mix, there is another complexity bound, but which will depend on some random variable, because we pick the pivot uniformly random. So the randomization cannot be used for the guarantee of the quick cluster. So to have this sample complexity, essentially we need to separate the procedure, threshold bandit and quick clusters procedure.
I see. Thank you.
Thank you.
Any question? If there's no, let's thank the speaker.
Thank you very much.